All right, welcome back. This is part two of organic chemistry. We're referencing chapter 23 in the Julia Burge book, Chemistry, 5th edition. Today, what we're going to talk about is organic compounds. We're going to pick up where we left off with functional groups that help determine the chemical and physical properties of the substance. And then we'll look at naming those functional groups, and we'll see. We may get to isomers today. We'll see how far this goes. So last time we talked about the backbone structure of an organic compound, and that's the carbon chain. Um, and then we talked about cyclical organic compounds of carbon and hydrogen, and if the electrons are delocalized as pi bonds above and below the axis of bonding, then we call those aromatic hydrocarbons. So um, today we're going to again focus on these long chains or these chained hydrocarbons with a functional group. And the functional group we're looking at here is the hydroxy group. And so the hydroxy group is the OH group. You might think of it as like sodium hydroxide, but we think of it as just the hydroxyl group. Okay, so why is it hydroxyl? Because it's OH, and then it has a bond coming off of it, and that bond is going to the carbon. So we'll call it the hydroxyl group. So you look at the chain of carbons. This carbon chain is 2 carbons long, and so we know that that comes from the aliphatic compound ethane. If we knock off the hydrogen that was here and we add this hydroxyl group, now it's an alcohol, and so we call this ethanol or ethyl alcohol. You'll hear it called both. Um, the preferred name, I believe, today's name should be ethyl alcohol. I mean ethanol. Then we have same thing. The chain here is 3 carbons long, so now we go. That's propane. And again, if you don't remember these, you're going to have to go back to chapter 2 and look at those the names for hydrocarbons: methane, ethane, propane, butane, and so forth. And again, we knock a hydrogen off here, substitute on a hydroxyl group, and we have 1 propanol. Now, the reason why we have to say 1 propanol is, again, we number these carbons with the lowest numbers so that where the substituent group is, that is at the lowest carbon. So we wouldn't call this 3 propanol. We would label this carbon as number 1 to reduce the number here, and we would call it 1 propanol. And if we attached it to the other end over here and we made this the OH and this the H here, it would still be 1 propanol. It would be the same thing, right? So then there is another type of propanol, and that is where the hydroxy group would be attached here, the hydroxyl group. And so if we do that, we would call that 2-propanol. So, or the common name would be isopropanol, right? So that's what we're looking at. This is a preferred name to say where is the substituent at the lowest carbon, and then the all tells us it's an alcohol, and the prop tells us that it's 3 carbons long. So here's another example. We look at our longest chain of carbons. That's 4 carbons, so we know that comes from butane. We've knocked off a hydrogen, substituted in a hydroxyl group here. And so this is carbon number 1. This would be carbon number 2 to give us the lowest number here. And we would call this 2-butanol. Next example, look at the longest chain. 1, 2, 3, 4, 5, and we could go 6 here or 6 here. Just keep it this way to make it easy. So 6 carbons long, and we see a methyl group attached to the second carbon, and we see a hydroxyl or a third. Let's see. There's a mistake on this here, I believe. Let's see. Yeah, there's a mistake. Well, okay, and then this is the hydroxy group here, hydroxyl group, okay? So in this case, um, the hexanol is last, so that chain is the long, and so we know it's of the compounds alcohols, all right? And so we are going to label this carbon as 1, 2, 3, 4, 5, 6, because it is a hexanol, it's an alcohol, and methyl then takes the 5 position. So to make this number smaller here, the methyl has to be 5, and so we would call this 5-methyl 3-hexanol. All right. So then we look at the next functional group that's attached. And so here we've knocked off a hydrogen off methane, and we have this functional group. And so the old name is acetic acid. You'll still hear it called this, but if you wanted to use a more proper name, that would be ethanoic acid. So it's 2 carbons long. It comes from ethane. And on the ethane, we've knocked off these hydrogens off this carbon and added a double bonded oxygen and a hydroxyl group. And so this would be called ethanoic acid. Same thing here. We see this functional group. It's carboxylic acid. Again, that's what identifies it, double bond or to the oxygen, a carbonyl group with a hydroxyl group. And so it's 3 carbons long, so we call this propanoic acid. And that would be, but it's also called propionic acid. So either one, but I prefer this name. It depends on your instructor and so forth, but I do like the newer names better. Same thing here. This is 4 carbons long. You see the functional group that tells you it's a carboxylic acid, and so I would call that butanoic acid. But the old name is butyric acid. And you think of butter, and this, when butter becomes rancid, we get this smell like that. And so that's where you're going to hear the word butyric acid. Okay, last one. So the carboxyl group is here. We're going to label this carbon as number 1 because this is a hexanoic acid. It's 6 carbons long. 1, 2, 3, 4, 5, 6. So we would say 5-methylhexanoic acid. So the functional group, this takes precedence. This carbon's going to be number 1. And so that makes the methyl group on the 5th carbon here. So 5-methylhexanoic acid. Again, what I want you to get out of this is this functional group that I've got circled. Make sure when you see this that you know it's a carboxylic acid. That's the type of organic compound it is because it has the carboxyl group on here. And then you go by the chain of the carbons. All right, so esters, very important compounds. And so that ester has a carbonyl group and a oxygen. We've knocked off the hydrogen here. So it looks like a carboxylic acid, but instead of putting a hydrogen in the blue box here, we put an alkyl group. So alkyl, carbon hydrogen based compound, or attachment, if you want to say it that way. And so here we have, this is 2 carbons long, so that's ethyl. And then over here, this part would be the acetate. So all of this in yellow is called acetate. So we would call this ethyl acetate. Same thing over here. This is 3 carbons long. This is where the carbonyl oxygen is. And so we would call this propionate. And then we would say attached to the other side of this oxygen here instead of a hydrogen, it's an alkyl group. We know that's the methyl group, so we would call this methyl propionate. So what I want you to get out of the esters, they come from the acids, the carboxylic acids. This is the old names. And then we substitute the hydrogen that would be on the carboxylic acid with another alkyl group, and that makes it an ester. And esters, again, a lot of them have distinctive odors, and they're interesting to work with in the lab. All right, so the next group of compounds, you see the carbonyl group here, but instead of having an OH group, you just have a hydrogen. All right, so the distinguishing mark of an aldehyde is carbonyl group, that's the carbon double bonded to the oxygen, and a hydrogen off on one side. Notice they all have this. And that group of compounds with this functional group is called an aldehyde. All right, so these are all aldehydes. Now, there's the newer name. This is an older name. I still like the newer name. So this one's ethanol. And so it tells me it's 2 carbons long. That's why I like this. And I know because it has an AL ending that it's an aldehyde. So propanol, I know it's 3 carbons long. I know it's an aldehyde. It's got a hydrogen on the other side of the carbonyl bond. So propanol. Butanol, again, 4 carbons long. Hydrogen on the other side of the carbonyl group, double, and then we got this carbonyl group again. Make sure you can speak the language here, butanol. And then the last one here, you look at this long chain and you start thinking like, okay, what's the identifying component? Well, it's definitely this, okay? And so that's where the attachment is. So we're going to label this as carbon number 1, this one 2, this one 3, this one 4, this one 5, this one 6. And so it's a hexanal. So that's that part. And then the methyl is attached to the 5th carbon, so we would say 5-methylhexanol. All right, next group is a ketone. So a ketone, again, it looks like a kind of a carboxylic acid. If this was an OH here, that's what you would have. But what we have is the carbonyl group. And then you say, well, is that an aldehyde? No, because in this compound, you're going to have R groups attached to the carbonyl carbon on either side. So there's no hydrogen attached to one side. It's always going to be an alkyl group attached to both sides of the carbonyl group here. So that's what makes it a ketone. So again, identify where the carbonyl group is and then describe what's attached here. So you have a methyl group here and an ethyl group here. And so E comes before M, so we call it ethyl methyl ketone, and that's the old name. The new name is just to say, okay, it's 1, 2, 3, 4 carbons long, and you call it 2-butanone. So again, this is propanone, this is 2-butanone. I like the newer system. Again, it's up to what your instructors are using, but the newer system, I think, is a little easier. When you hear the word bute, you know it's 4 carbons long, and then the 2 tells you where the carbonyl group is. And with propanone, it has to be here, so we don't have to put a 2 here because that's the only place it can be and give you alkyl groups on either side. This one, you look at that part, okay, if you want to go by the new naming system, this is 1, 2, 3, 4, 5, 6 carbons long, so you know it's hexanone. We want this we want this part that defines the compound to have the lowest carbon number. So there's 1, 2, 3, so that's 3-hexanone. This is the 4th carbon, this is the 5th carbon. On the 5th carbon we have this alkyl group, the methyl group, and so we would say 5-methyl-3-hexanone. All right. So you can kind of see I hope you're seeing what's going on here, that we've kind of started with a carboxylic acid. We knocked off a hydrogen off the OH, the hydroxyl group, and we substituted an R on there, another alkyl group, and it became an ester. And then we knocked off the O and the H and just put an alkyl group on there, and it becomes a ketone if it's an alkyl group on both sides. If it's just a hydrogen on one side, it's an aldehyde. And all of these have different chemical and physical properties. All right, so we've talked about the functional group amine derived from ammonia. We've knocked off a hydrogen. Now we have a bond here. This is where we get a bond between the nitrogen and the carbon. So you can see that this is an amine. Looks like ammonia, and it's attached to an alkyl group. So ethanamine, that's a new one for me, ethanamine, all right? And then here you could have the amine group attached to either a terminal carbon. If that's the case, this is carbon number 1. If it's attached to this end, it'd still be carbon number 1. It'd be the same thing. So we want to say that it's attached to the end, so we call it 1-propanamine. And again, the older name is propylamine. This is ethylamine. You do hear them called that. That is the more common name, ethylamine and propylamine. But I would get used to calling them by these newer names. All right, last one, 2 down there. Let's look at them. So again, this is a terminal amine. This is going to be the carbon number 1 here. And so we would say it's 4 carbons long, 1 butanamine, all right? Or butylamine is another name for it. But the 1 tells you it's on the terminal end. Doesn't matter if it's on this end or this end, it's still going to be 1 butanamine. And then you notice if it's on the second carbon, it doesn't matter if it's on this one or this one, and then that's going to make it a 2-butanamine. All right. So the next one here, our longest chain, they generally try to make it like this. But so we got 1, 2, 3, 4, 5, 6 carbons long. And you see the functional group amine here. So it's hexanamine. We're going to since the amine's on this end, this is carbon number 1, 2, 3, 4, 5. And so we would say 5-methyl 1-hexanamine. All right. So I hope that makes sense. I hope you see the pattern, whether it's a ketone or an aldehyde or alcohol, the naming system that we use. Now you're saying, I don't really get this. You got to read the book. You got to read this section of the book, and it has all the instructions on how you name these compounds by their again, the newer name, I think that's what you're going to generally focus on. All right, so then an amide. So an amide is all of this. This is the functional group. Remember what makes the difference between an amide and amine? It looks like an amine, but you've added a carbonyl group. All right, looks like an amine, but then, there's a carbonyl group. That makes it different. That makes it an amide, all right? And again, you think of peptides when you're looking at this. So this carbon's 3 carbons long, so propanamide, all right? This one's 4 carbons long, butanamide, all right? So I think I still like the newer names better. It's easier. You see how many carbons it is. Pick out the right prefix for that number of carbons and then add amide to the end of it. And these are primary amines, or amides, I should say, primary amides. And that's because the nitrogen is attached to 2 hydrogens, and then it just is attached to the carbon here. And then this carbon is attached to only 1 other carbon here. All right, it says many compounds contain more than 1 functional group. Okay, So we have an amino acid. So here you see the carboxyl group, and here you see the amine. Here's the common name, alanine. All right? So that's an amino acid. Again, this amine gives it away, right? And then the acid part, this is a carboxylic acid. This is a carboxyl group, which makes this a carboxylic acid. So we got the amine group here, and we got the group here that makes it an acid. All right, so let's see if we're getting the hang of this. So I want you to identify the functional groups in each molecule. Okay, so circle them, tell me what you have, and let's see where you are here. So stop. This is aspartame, artificial sweetener, and you should be able to identify the different functional groups attached to that compound. All right, have you circled them? If not, stop the video, write this down on paper, and circle your functional groups. All right, welcome back. So let's look and see what you have here. So right off the bat, you see in a primary amine right there, okay? You see a carboxyl group right there. You see an an ester, and that's going to be this part in here. All right. And then you see an amide right there. So we got 1, 2, 3, 4 functional groups on this compound. 4 functional groups. So that's what I want you to be able to do, is look at something, look at a big compound like this, big molecule, and start identifying functional groups on that. So you can see the chain here, the backbone. We're looking at something like that. There's a nitrogen there, carbon, 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 carbon. And then we're looking at what's attached to it there. All right, let's see if we're right here. Let's check on the next slide. That's what they've got highlighted there as well. Okay, let's get another shot at it. Okay, you're looking at this one, a little easier, right? Identify the functional groups of salicylic acid. Well, what's this group right here? Carboxyl group. What is this group right here? A hydroxyl group. So we have 2. Okay, let's look at this one. So what do you see? Well, you definitely see an amine, right? The rest of that, just a long chain hydrocarbon, right? So we definitely see an amine. This is amphetamine. So see, you hear the word amine right there. That's the common name, amphetamine. Oops, back. Okay. So if you can't do these last couple of problems, what that means is you need to go back and look at the functional groups. And what I would say to do is go back and really focus on the table that was listed as the different functional groups. Okay, so look at this table of 23.2. Okay, 23.2. And again, the difference between primary, secondary, as we remove the hydrogens and we add alkyl groups, it becomes from primary, where it's 2 hydrogens attached to the carbonyl group. Same thing up here. When it's all NH2s, it's primary, but once you substitute one of the hydrogens for an alkyl group, this one has two alkyl groups, it's tertiary. Same thing here. This is primary. Knock off a hydrogen, put in an alkyl group, it's secondary. Knock off another hydrogen, put an alkyl group, it's a tertiary. So focus on that. Really get this table down, and then come back to this and start looking at the functional groups and how we name them, how we name the compounds with these functional groups. Be able to identify functional groups attached to a carbon-hydrogen backbone. All right, so the next section, 23.3, is how do we write these? How do we convey to other chemists or other scientists what the structure of the compound looks like? So we have the chemical formula, we have a structural formula, we have a condensed structural formula, and so we're going to talk about different types of formulas here and what do they convey and why would we use one formula over another. And then we're going to bring back resonance that we talked about in chapter 8. In chapter 8 in Bird's book. So again, if you're having trouble with Lewis structures or remembering what resonance is or formal charges, then you may want to review chapter 8 before you continue on here. All right. So it's all about information, right? So the simplest formula here is a molecular formula. It just tells you how many carbons and hydrogens are in this compound. So we call it a chemical formula or just a molecular formula. Molecular is actually giving us some information. Molecular tells us that we're dealing with a covalently bound substance, okay? So we before just called it a chemical formula. Here they give you a little bit more information. They say it's a molecular formula, so we know it's covalently bound. That doesn't show you how the carbons are attached or how the hydrogens are attached to the carbons. If I want to do that, I have to do a structural formula. So I have to know more information. And the more information you know is, you know carbon wants to form 4 bonds. And so these 3 bonds are going to be hydrogens. And then that carbon's going to bond to the next carbon. There's going to be 2 hydrogens coming off of that carbon. And then there's going to be 2 hydrogens coming off that carbon. And that's going to keep happening until you get out here to the end. And then you're going to have 2 hydrogens attached to this carbon. And then the terminal carbon, you're going to have 3 hydrogens attached. So this is called a structural formula. You can visually see that the carbons are attached to each other and the hydrogens are attached to the carbon based on, you know, that carbon wants to form 4 bonds. Takes up a lot of space though. So this repeating structure of CH2 that you see, 1, there's a typo here, 2, 3, 4, 5, 6 times. A condensed structural formula is you would put the CH2 in parentheses and then as a subscript, how many times does that unit repeat itself, and it would be 6 times. So that's called a condensed structural formula. We like this because it does convey the structure, but it doesn't take up as much space. Now, here's a model. Here's what we call a ball and stick model of octane. And so, again, molecular formula of octane, structural formula of octane, condensed structural formula of octane, and now we have a ball and stick model of octane. So what I like about the ball and stick model is you can see that's a tetrahedral structure right there. That's an AX4. That's tetrahedral. You can see this is tetrahedral. It's AX4. It's 2 hydrogens bonded to the carbon, and it's bonded to 2 other carbons. So all of these are AX4 classifications. They're all tetrahedral molecular geometries. And then the next thing you can do, which is really important in organic chemistry, you can tell me that the hybridization is sp3. All right, sp3 hybridization. So 4 things coming off the central atom, we're going to have an sp3 hybridization there. So the ball and stick model gives you even more information. It gives you a visual idea of what the molecule looks like. You notice that it's zigzag. It's not a straight line like these formulas up here try to convey. And so that's the advantage of a ball and stick model. Gives you a lot more information. But in order to do a ball and stick model, you have to know Lewis structures and you have to know molecular geometries. And you should know these, but and if not, again, go back to chapter 8 and 9. You're going to have to refresh your memory. But that's where this comes from. But it takes up a lot of space and a lot of time. And to make it look like this, you're going to have you have to have some computer program to do that. So is there an easier way to convey this? Well, we're going to see that in a minute. Okay, so here we go with another. The molecular formula is this. But notice in this one, the long chain is 1, 2, 3, 4, 5, 6, 7 carbons. And now we have a methyl group attached to the 7 carbons. So this is not the same compound that we saw on the last slide. This long chain is heptane, not octane. So you have the molecular formula looks the same. The structural formula looks different. And we can see it's different. And then again, we see a repeating values here. So let's break this down. You have the CH3, there it is. Then you look at this carbon, and there's a hydrogen attached to it, and there's a methyl group attached. So there's the hydrogen, and then in parentheses, you have the methyl group. Then you have a repeating 1, 2, 3, 4 of the CH2 groups, right? And so that's why we have this in parentheses 4. And then the terminal carbon has to have 4 bonds. This carbon's attached to one of these carbons, and then it's attached to 3 hydrogens. So you should be able to look at this and go, okay, I know that there's a carbon and it's attached to 3 hydrogens. I know this carbon has a hydrogen attached, and I know it has a methyl group attached. And then that's attached to the next carbon. So that's what this is telling you right here. You know it's got to have 4 bonds. One of the bonds is hydrogen. One of the bonds is the methyl group. And then it's attached to this carbon, and it's attached to one of those carbons. All right. So then we go out, 4 carbons here, and then the CH3 on the end. 1, 2, 3, 4, 5, 6, 7. And then on this one, you're going to have the 2 hydrogens and the rest of these, or 3 hydrogens on the terminal and 2 on the rest of these. All right. So again, molecular formula, not as much information. We can see that molecular formula doesn't tell us whether it's heptane or octane or whatever. It just tells us how many carbons. It's empirical formula of how many carbons to hydrogens. Well, not empirical, I shouldn't say that. It is the empirical formula for this one, but it is the molecular formula. Empirical is the simplest whole number ratio, but since there is no simplest whole number ratio here, that is the empirical formula too. But the molecular formula tells you how many carbons and hydrogens are in the compound, all right? So that tells us to, and then knowing that it's got a methyl group, that's how we know it's this. If they don't tell us, we would have written octane. We wouldn't have written this, right? Okay, and so again, ball and stick model, this constituent, this alkyl group is on, we would label this carbon number 2 to make it the lowest carbon. This would be 3, 4, 5, 6, 7. So it's a heptane, and then we've got the methyl group attached to the second carbon. So 2-methylheptane. All right. So the Kekulé structures. So Kekulé, his fame is that he was the one he dreamed that a snake was biting its tail. And he's the one who came up with that benzene is a hexagonal ring like this. All right. That the snake bit its tail, and therefore that is why he came up with this cyclical structure. So a cuticulae structure, it looks a lot like a Lewis structure, but notice you don't put in your lone pairs. You're looking at the structure, it's laying it out for you, but you don't put in the lone pairs. Okay? So, again, why are these great structures? They identify very easily, start to help you to identify what kind of compound these are. So this one you know is an aldehyde because it's got the carbonyl group and a hydrogen. And this one you know as a carboxylic acid. You can see that very readily here. And we would call it acetic acid. Or ethanoic acid if you want the newer name, and then we have ethanol over here, or also that's the newer name, the old name ethyl alcohol. All right, so very common that we do these. We like these because we don't have to worry about the lone pairs and so forth, but it does give us a nice structure and it helps us identify the functional groups. Now is this is the newest way to write formulas that convey more information than just a molecular formula. I don't believe I had these when I went to school, undergraduate. I don't know if that's just my professor. Surely they've been around a long time. But this is called a bond line structure, all right? Bond line structure. Straight lines that represent carbon-to-carbon bonds. And I think you're going to like this one the best. Once you learn how this works, I think you'll say, this is my favorite way to draw the structure. Because it conveys information more so than just a molecular formula, but it doesn't take up as much space, or it's not as detailed as a structural formula. So, although it's very similar to a structural formula. So let's look at it. So instead of doing a structural formula where we have 5 carbons long, we know the terminal carbons are CH3s, methyl groups, and then you have the CH2s in the middle here. At the end, you know there's a carbon. Every one of these points is a carbon, right? And so it's kind of like, it's starting to kind of look a little bit like a ball and stick, right? You know that there's 3 hydrogens coming off here, and they're coming off at 109.5 degrees because it's a tetrahedral. But we don't need to write that. And we don't need to put the carbons in because we know at the ends there's carbons, and each one of these points there's a carbon. So that's the advantage of a bond line structure, is that you just draw lines. It's understood that this carbon has to have 4 bonds. There has to be a hydrogen attached here, and there has to be a hydrogen attached there. Same thing down here for this carbon to have 4, and the same thing up here. And then the ones on the end, they have to have 3 to make it 4 bonds on the carbon. So that's the advantage of the bond line structure. Very quick to draw. Don't have to worry about the hydrogens. It's understood. And so again, if we look at this, we know it's 1, 2, 3, 4 carbons long. Right there it is. 1, 2, 3, 4 carbons long. And then this line goes up here, terminal. Terminal tells you it's a carbon, and then that carbon has to have 3 hydrogens attached to it. Not bad, is it? Not bad. All right, so this next one down here, it's 3 carbons long. Right there it is. 1, 2, 3. And then a straight line here tells you there's a carbon here and a carbon here. And each one of these terminal carbons has 3 hydrogens attached. So this is neopentane. Neopentane is the old name, neopentane. All right, and it is, the reason why I call it neopentane is because it does have those 5 carbons in there. Again, old name. All right, so then what do you do when you have a double bond? Well, it's 3 carbons long here. Propanone, here it is, 1, 2, 3. Double bond, here's that carbonyl group. You just put a double bond on an oxygen. We don't worry about the electrons like the cuticulae structure. And so we're not worried about the lone pairs. We're just trying to get a structure of what it looks like, and for us to look at that structure and go, oh yeah, this is a ketone. And how do we know it's a ketone? Because these are both carbons on this end, and so we know ketones are a carbonyl group with alkyl groups on both sides. All right, ethylamine, ethanamine, again, 2 carbons, so that gives us the ethyl part, or etha, and then we know that this functional group is amine, so ethanamine or ethylamine. And then look at this structure, tetrahydrofuran. This has an oxygen at one of the corners, and then the rest of these corners are carbons. And again, looking at that carbon, you know there's got to be 2 hydrogens attached. All right, same thing here, same thing here, and then same thing here, right? So 2 carbons. Maybe I did that one wrong. Maybe it should be down like that. But you know there's 2 carbons attached to each one of those carbons for it to be for it to have 4 bonds coming off of it. So bond line formula. Now here's what I will say I see students do. If they ask for a bond line formula and you put a carbon, a C here or a C here, it's going to count it wrong. You are starting to blend different model sets together. All right. So if they ask for a structural formula, you're going to draw it all out like that. If they ask for a condensed structural formula, well, none of these really lend itself to a condensed structural formula, so you really can't change those. But if they ask for a bond line formula, do not put carbons in or hydrogens in, because if you do, it'll count it wrong because you're not using the formula correctly. Okay? So just be careful. Read the question. What is it asking for? Molecular formula, structural formula, condensed structural formula, and that's the one probably most missed actually, condensed structural formula, and then bond line structure. All right, let's see if you can do these. Okay, let's see if you can do these. It says write the molecular formula. I think that's going to be easy, right? And the structural formula or condensed structural formula for the following. So you got A and B there. All right, so stop the slide here, stop the video, see if you can do this. And I think everyone should get the molecular formula, right? Everybody should get the molecular formula. If not, we've got some problems. But I do think you might have a little bit of problem with condensed structural formula. Maybe, hopefully not the structural, but maybe the condensed structural. All right, so let's stop and look at that. All right, welcome back. So this is what I would do. If I want to make sure I get this right, we know there's a carbon here, a carbon here, a carbon here, and a carbon here. We know there's 3 hydrogens here, there's 3 hydrogens here. How many hydrogens on these 2 carbons here? Should just be 1, right? Because you got the double bond here, you know carbon's got to have 4 bonds. There's 1, there's 2, there's 3. That only leaves 1 place for a hydrogen to attach. Same thing down here. All right, so when you write this, you know it's 4 carbons long, so it's C4. You know it's 3 and 3 and 2, so that's going to be C4H8. C4H8. This one over here, you know it's a carbon here, you know it's a carbon here, you know there's 3 hydrogens attached to that carbon to give that carbon 4 bonds. This carbon's already got 4 bonds, so this one you're going to have a C2, you're going to have an H5, an O, and an NH2. Okay. So let's see how they drew those. C4H8, C2H5NO. Oops, did I write that wrong? Let's see. Yeah, I did. Crap. Let's see what I did after I did that. Let's go back. We don't need this, right? We don't need that. And we'll put the N in here and then the O here. Okay, I'll go with that. All right. We saw it, right? So you make a mistake. 1, 2, 3, and those two there makes that a 5 there. All right. So you can make mistakes just like me. And so there you go, C2H5NO. All right, so then that's the molecular formula. Now the structural formula, they write a condensed one for this one because you have a repeating structure. This is CH, this is CH. So they went CH3, CH, there's two of them, and then CH3 at the end. So there's your condensed structural formula. We're just called structural formula. You can, either way, I would call it a condensed structural formula, but they're both structural formulas. This one you don't have a repeating thing, so it's CH3. You see the carbon. All right, so this is what this tells you. This carbon's attached to that carbon. This carbon has to have 4 bonds, and when you see a C and an O together, you know it's double bonded to the O, the oxygen, and then this carbon's attached to the nitrogen, and that gives you the 4 bonds for the carbon. Okay, and then the amine group is NH2. So just keep that in mind. The bottom line is carbon's got to have 4 bonds. It's got to have 4 bonds. You got to show me that what's it attached to. So whatever's trailing after that carbon is what it's going to be attached to, and at least the carbon in front of it, all right, or whatever's in front of it. It's got to be attached to give you a total of 4 bonds. If it wasn't attached this way, you wouldn't have this linkage here, all right? And then this carbon, again, so it's got to be attached to that. It's got to be attached to the nitrogen, and you got, well, it's got to have 4 bonds, so it's got to be double bonded to the oxygen there. All right, so just be careful with that. I think that's a common mistake. All right, so resonance. We talked about resonance in Chapter 8. It's let me again define what resonance is. You follow the rules for writing a Lewis structure. So if you don't remember how we do this, the quickest way to do a Lewis structure is you look at you count up your total number of valence electrons. So sulfur has 6, and you've got 3 oxygens, and they both have 6. If we add this all together, there are 24 valence electrons in this sulfur trioxide. Everything wants to have 8, following the octet rule. And so following the octet rule, we can come up with 3 structures. Now you say, is there a different one than these 3? There's one that doesn't follow the octet rule that gives you better formal charges, but we're going to follow the octet rule unless they tell us otherwise. So we have 3 structures. Which one of these structures is the correct structure? In reality, again, this is what I say in my Chem 170 class. None of these are correct. None of them. It is a failure of the Lewis structure theory. Because when we measure the length of between this nucleus of the oxygen and this nucleus of the sulfur, they're exactly the same length for all 3 sulfur-oxygen bonds. I hear some people say they rotate really fast. That's not what's happening. It's just telling us that Lewis's theory is failing here. So the way that we show these electrons being, so again, this is really what's going on if you want to think about it. The sulfur is here and this oxygen's here, and there's an oxygen kind of, this is all flat. Let me just assume this is all flat. You're going to have a pi bond where that double bond is, and it can be here. There's these delocalized electrons above the plane and below the plane here. Delocalized, all right? And so that's what's going on, is there's a cloud of electrons above the axial nuclei bonds, sulfur to oxygen, the sigma bonds, and that's what allows these electrons to be at different, different places at different, well, it allows them to be in somewhere in here. Let's just say that, somewhere in here. And again, Lewis's theory is failing. None of these are correct, but this is the best way we can do it. And when we see 3 structures like this, we call it resonance. All right? So, Again, this is trigonal planar. This is a planar structure. This is AX3. If you remember from Chapter 9, Molecular Geometries, this is a flat structure, trigonal planar. So in organic chemistry, what we like to do to convey this resonance is we use this little arrow thing. All right, the arrow. So what this is showing is this lone pair is going to become the bonding pair, and this bonding pair here is going to attach itself as a lone pair onto this oxygen. So that's what the arrows are used for, and you're going to have some assignments where you have to place these arrows into your structure. So here, between here and the next structure, this lone pair becomes, this bonding pair on the double bond becomes a lone pair, all right? And now you only have a single bond here. And this double bond here is created because this lone pair here moves to a bonding site, and now we have a bonding pair here. So we're going to use arrows to signify the movement of lone pairs to bonding pair positions. And they say, why do I need to know this? Well, when you do the formal charge, remember what formal charge, let's do it the formal way. So the formal charge on the single oxygen, OS, is equal to the number of valence electrons in a free atom of oxygen minus, and then in parentheses, 1/2 of the bonding electrons plus the non-bonding electrons. So if you look at this oxygen here, it would be 6 minus 6. All right, so there's a 6 minus, we have 6 here for the 6 non-bonding electrons, yeah. And then we have 2 bonding electrons. Remember, this line represents a shared pair. So the reason why you want to do this brackets is that you add up what's in the brackets first, sum that up, and then subtract it from 6. So 1/2 of 2 is 1, plus the 6 non-bonding electrons. That equals 7, and 6 minus 7 means the formal charge on this oxygen is a -1. All right? Now, let me show you the fast way to do this. If you're doing this on a quiz or a test, you're just going to go 6 is the valence electrons in a free atom. You're going to go 6 minus 1, 2, 3, 4, 5, 6, 7. That's how quick it can be done. Because notice this line is really a shared pair, and you're taking 1/2 of that pair, so that's like 1, right? So that's why it's 6 minus 1, 2, 3, 4, 5, 6, 7, and you get -1 for the formal charge. Now you don't reinvent the wheel. You know this is -1 as well because they're exactly the same. All right, let's do the one on this double bonded oxygen. You have 6 minus 1, 2, 3, 4, 5, 6. The formal charge on that oxygen is 0. And if you remember this from Chem 170, what's the formal charge have to be on the sulfur? Well, if it's a neutral compound, when you add these all up, it has to equal 0. So we know the formal charge on this sulfur has to be +2. Has to be. So that when I add -1 and a -1 and a +2 and a 0, I get 0. Now you can prove it. You can say 6 minus 1, 2, 3, 4. 6 minus 4, +2. There's no non-bonding electrons on here. So there's a total of 8 valence electrons around the sulfur. 8 times 1/2 is 4. Right there they are. 1, 2, 3, 4. And 6 minus 4 is a +2. All right. So it's really important that you can do this. And you're going, I'm really lost. I don't know what I'm doing here. I'm going to tell you, you're going to have to go back and read Chapter 8 and Chapter 9. If you don't remember this stuff from Chem 170, Gen Chem 1, you're going to have to read Lewis structures, and you're going to have to, this stuff here, this AX3, so most of this is out of Chapter 8. Formal charge, resonance, Lewis structures, all out of Chapter 8. But Chapter 9 tells us the classification is AX3, which tells us the geometry is trigonal planar. And then the other thing it tells us is if you know this is AX3, then you know the type of bonding is sp2. All right? So that's what's important here. And the reason you go, well, why do I need to know that? Because there's this delocalized cloud of electrons above and below the plane of the sulfur and oxygen bonds. All right? That's why you need to know that. All right. So let's look at another structure. Now this is the one that throws students the most because we didn't show you anything like this in Gen Chem 1. So we're dealing with, I mean, if I had a hydrogen out here, you know, then I'd have a carboxylic acid, right? But what we're doing, we're focused on what's in the brackets here. And the question is, we always draw the double bond here, but could the double bond be on this oxygen instead? Absolutely. Sure it could. So what we would be doing here is taking this double bond and moving the electrons into a non-bonding pair on this oxygen, and that's what we did. And then we take a non-bonding pair on this oxygen and move it in between the carbon and the oxygen. And then you go, why would you do that? Well, you got to have 4 bonds coming off that carbon, right? So there's 1, there's 2, there's 3, there's 4. So that's why this happens, is that you have to have 4 bonds on the carbon. And if you do the formal charges, you'd find out this is 0, this is 0, this is 0, this is 0. This is 0 with the double bond on the oxygen here. This is 0 on the carbon here because it's got 4 things coming off of 4 minus 4 is 0. And then 6 minus 7 makes this the formal charge on this a -1. And notice that adds up to the actual charge on the entire substance. So here, the formal charge would be -1 up here. This would be 0. And again, when we add this up, these are all zeros. And that equals that. And so we're fine. This oxygen's -1, the single bonded oxygen, the overall, and that matches the overall charge on the ion, which is a -1 here. Go this way. That's a terrible arrow. All right. Okay. So, so that's what you're doing here. That's what you're doing. So same thing here. This is not the same thing, right? These are not the same structure. These are resonance. I agree with that, but this is not. All right. So this one, there's an oxygen totally gone. And so we have a hydrogen here. And so, again, though, this oxygen is 6 minus 7. There is a formal charge of -1 here. And then the overall charge on this ion is a -1. So that's what we're looking at here. That's what we're looking at. All right, so if you understand now what we just talked about, it says draw all possible resonance structures for the hydrogen phosphate ion. So the hydrogen phosphate ion, we talked about this in Gen Chem 1. This is a polyatomic ion. You know that the phosphorus has to be the central atom. Why? Because it's the least electronegative, and hydrogen may be less electronegative, but hydrogen can never be the central atom. So we had the phosphorus in the middle, the oxygens are attached to it, and then the hydrogen is attached to the oxygen. And that's what makes this hydrogen slightly acidic. All right? Non-metal, here's a way to remember it. Non-metal hydroxide. Those are acids, non-metal hydroxides. All right. So the first thing we're going to do is we're going to draw a Lewis structure, the complete Lewis structure. So how do we do that? Well, it's 1 valence electron for the hydrogen. It's 5 for the phosphorus. It's 4 times 6 for the oxygens, because there's 4 oxygens. Each one has 6 valence electrons. And then we got to add 2 electrons because it's a -2 charged ion. So 1 plus 5 is 6. 6 plus 24 is 30, plus 2, 32 valence electrons. 32 valence electrons. So we got to put in 32 valence electrons so that everything feels like it has 8, according to the octet rule. So we know there's going to be 3 lone pairs on each one of those oxygens, and there's going to be 2 lone pairs. Let me erase that so it's not confusing. Oops. This part right here, let me erase that. Oops. And then we've got 2 lone pairs here. All right, so there's your structure. You've done the Lewis structure correctly. So you can see if you can't do a Lewis structure, you're going to be really hurting in this class. So again, you may have to brush up on chapter 8 and 9. That's no big deal, okay? Because you need to know Lewis structures. Those you plan to go on and take organic chemistry, you have to have Lewis structures, formal charge, molecular geometries, hybridizations. That stuff has to be mastered in order to have fun in organic chemistry. All right, so here's what we have. And then you're looking at that and you're going, why can't the double bond be here? Or why can't the double bond be here? So that's what we're looking at. So it says used curved arrows to indicate how electrons are repositioned and determine the positions of the negative charges. So if this moves up here, so there's an arrow, then this is going to have 3 lone pairs around it, and it's not going to have the double bond, and the formal charge will go from 0 to a -1. And then if the double bond goes here, that means a lone pair is going from here, and it's going to make the double bond. That's going to have the 0 formal charge, and this is going to have the -1 formal charge because nothing changed on it. We didn't put the double bond yet. So that's what you're doing here. So you get the Lewis structure, and then you start playing with it as far as where can that double bond go. So these are the easy ones, right? That's the one we just showed. Then we could do it this way, and then we can do it this way. So the double bond is kind of from here to here to here. All right. And then the last one, this, and again, these aren't following the octet rule, right? This is 2, 4, 6, 8, 10 electrons around it. Can phosphorus have 10 valence electrons? Yes, it can. Because phosphorus is in period 3, and period 3 has the unfilled D sublevel, and so it can have more than 8 electrons around it. So this last one, phosphorus is following the octet rule. But watch what happens here. Phosphorus normally has 5 valence electrons, and this one it only has 4 around it, so that's why it's a positive charge here. Each one of these oxygens has 1 more electron than it should. That's why these are negative. And the OH hasn't changed here. So there are 4 resonance structures here. The first 3 do not follow the octet rule. The last one does. Now, the question is, which one of these Lewis structures are the best? Would you say this Lewis structure is better than these? And I would say no. Because we want to minimize the formal charges, and these minimize the formal charges. Although you could argue, well, this is more electronegative, it should be pulling the electron off the phosphorus, but I would, the general rule is we want to minimize the formal charges. All right? That's a good one. It's a good one. So again, let's kind of rehash this one more time just to show you what's going on. So it says draw all the possible resonance structures for hydrogen phosphate ion. It doesn't give us the restriction that it has to follow the octet rule. And that's what you should read there. Sometimes it'll say follows the octet rule, sometimes they don't. This one just says all possible. So it's wide open. So right off the bat, you're going to say, well, 3 of the structures are, this double bond is going to be here, this oxygen, or that oxygen. There's 3 resonance structures right there. And then the 4th one comes about by, is there something else possible that has 32 valence electrons? Here's the rules. It has to have 32, no more, no less. Is there a way you can draw a structure that has 32 valence electrons and it follows the octet rules? or it follows the rules. So let's make sure this is right. There's 8, 8, 8, and 8. Yeah, that's 32 valence electrons. Yeah. So you can do it that way. And then you're going to use the arrows to convey where the shifts are. Double bond is leaving here and becoming a lone pair, and that's what we see here. Lone pair is leaving and becoming a double bond here. So that's why you got to be able to draw these arrows. And there's an arrow. When you do these on ChemDraw, you'll see on the left-hand box of the tools, there's an arrow box, and you put that in. Now, the formal charges on ChemDraw, you either have a positive or a negative. I think that's all they have. And so you put a positive where the formal charge is one less than it should be for a free atom, and you put a negative where the formal charge is one more. So I guess they're going to limit you on what the formal charges are going to be. All right. So let's just wrap up this lecture. It's about functional groups. It's about naming compounds with functional groups. Again, the functional groups make the compounds classifications like alcohols, carboxylic acids, esters, aldehydes, ketones. And then we can have functional groups off of those groups of compounds. And then this last part is about models. We have the molecular formula, doesn't really give us much information, just tells us how many carbons and hydrogens are in these carbon and hydrogen compounds. We have the structural formula, it gives us a little more information, tells us it's a straight chain and it's got the, how many carbons long it is and how the hydrogens are attached to the carbons. Then we have the condensed, if there's a repeating structure in there, we can put that in parentheses, condense the formula. Then we have the ball and stick model. That gives us more information, but you have to know molecular geometry in order to get that correct. That is tetrahedral for all those carbons. And then we have the line bond formula. That's the way I see most stuff done today. It seems like it's more popular than the other ones. But it can be tricky as well if you don't understand what the lines and corners mean, or how do you put the functional group onto the line structure. Do not, like I said, blend condensed and line, otherwise it'll count it wrong. Then we talked about resonance here, and the thing that they want you to learn about resonance is using the arrow to show the movement of the electrons from maybe a double bond or a triple bond into a lone pair or vice versa, and then be able to describe those resonance structures. And again, that means you're going to have to know formal charge. And I've shown you the formal way to do it and the quick way to do it. And again, if formal charge is new to you, you're definitely going to have to go back to chapter 8 and read about formal charge. So we're going to stop here, and then I'm going to have one more video, and that's going to be over sections 4 and 5, which is on isomers. So isomers, there are different types, but you're going to find that different. I mean, we saw it here. We saw where you have the same chemical formula, but different structural formulas. Like we saw octane and heptane, whatever that was, 2-methylheptane. And they have the same chemical formula, but they are different structurally, and they're going to have different chemical and physical properties. All right.